So today I'll be talking about false discovery rate control, or it's specifically local false discovery rate control. So this is joint work with two students, Jake Soloff and Daniel Yixiang. Jake was at Berkeley, is now at UChicago, and Daniel was at UChicago the whole time. So just to motivate the talk, one thing I'll be arguing today is that the false discovery rate is not quite as appropriate a metric for error control as we sometimes think. So if we think about why people usually justify the false discovery rate control, if you're teaching a course and you're going from family-wise error rate control to false discovery rate control, is the idea of a cost-benefit trade-off. So false discoveries waste resources. So in particular, if you can control the false discovery rate at less than 5%, then you're spending no more than 5% of your investment, say in follow-up studies, chasing down false leads. So you might say, all right, so then as long as a false discovery is no more than 19 times more costly than a false non-discovery or a type 2 error, then I'll be happy with the false discovery rate being less than 5%. So the problem, however, is that the false discovery rate really controls the average utility of the rejections. So if we say that we only think that about 5% of the rejections in our list are false discoveries, we might actually have a good idea of which 5%. And so some rejections can be very bad. So just to show you an example of what I mean. So here, this is just a simulation where we generate just some uniform random variables, IID uniform random variables. So the uniform p-values, and the BH procedure at say 0.2 appropriately is not going to make any rejections because all of these p-values are null. But what happens if we just add 200 more p-values that are all exactly equal to 0? So the Benjamini-Hochberg procedure is definitely going to reject those 200, but then it's actually going to treat itself to 19 more rejections to bring its estimated FDR budget up to what was requested, which was 20%. So it's a good idea, let me get out of your way, it's a good idea that we're rejecting these 200. They're definitely non-nulls, but for the remaining ones, we still have every reason to believe that, and in fact, we know we have private knowledge, gold standard knowledge, because we generated the data ourselves. But even if that weren't the case, we have every reason to believe that these p-values look to be on just a straight linear component of the ECDF. And so we have every reason to believe these are nulls too. So why are we rejecting them? The only reason we're rejecting them, again, is because we requested a 20% false discovery rate, and so BH is serving that up for us. All right, so this is kind of a perverse example where we're sort of trying to, we can view this as sort of a way of cheating by adding a bunch of extremely non-null hypotheses. We get to make a bunch of null rejections. But even if we're not trying to mess up the BH procedure, there can still be a wide variety of quality of rejections from the smallest p-values to the largest p-values in our rejection list. So in particular, if we just take the simulations from the BH paper from 1995, of course, if we run the BH procedure at level Q equals 5%, then we are going to control the false discovery rate, again, measuring the average quality of our rejections at 5%. But if we ask, well, what about the last rejection in the list, the one with the largest p-value that just barely got rejected? So in some of these simulations, the last rejection can be null about 30% of the time. We know it's going to be worse than 5%. That's almost a foregone conclusion. But how much more? It could be 30%, but depending on the parameters of the simulation, it could be 50%, 60%, or even 100%, as we just saw. So in terms of that, our colleagues in the economics department would say, we need to measure not just the average utility of the rejections in the list, but we really should be measuring the marginal utility. And we'll say this more precisely when we talk about decision theory a bit later in the talk. But right now, just at an informal level, if we're deciding where to place the threshold, then our concern is not what is the average quality of the p-values, but rather if we're considering making the threshold higher or lower, the question is what is the quality of the rejections that we would be including or excluding by raising or lowering the threshold. So we should really have more eye on the marginal utility rather than the average utility of our projections. Okay, so the main conceptual ingredients of this talk, first is to say, we're not just interested in the average quality of the rejections, we actually want to focus our attention on the least promising rejection, because the quality of the least promising rejection, knowing about that is what tells us whether we should be increasing or decreasing the threshold. The right tool for thinking about this least promising rejection is Efron's local false discovery rate, which just measures in a simple Bayesian model the posterior probability that a given rejection is null. Again, we can care individually about each rejection's cost-benefit analysis. So there are a lot of methods for estimating local false discovery rate. And the usual practice is to just sort of focus on this estimation and not necessarily consider very much about finite sample effects. But we don't know very much about, in a particular finite sample problem, if we use a method like this and say use it to set a rejection threshold, we don't really know what the finite sample effect in a procedure like that would actually be, at least not a priori. And in fact, we would have good reason to doubt that it will automatically do a good job, because when we're setting this threshold, it's going to be for some of the smallest p-values. And this is really this local false discovery rate really amounts to a density estimation problem, as we'll see. So we're estimating a density in the tail of the distribution, and so there's no guarantee that we're going to be doing a good job in finite samples. Second, we're going to make one main assumption, apart from independence, which is, of course, a large assumption, but we're going to make an assumption of monotone density. So in particular, we're assuming that under the null hypothesis, the density of the p-value distribution is decreasing. But that's just to say that smaller p-values are better bets. The smaller the p-value is, the stronger the evidence against the null. If that weren't true, we might ask, well, why did we choose this particular function as our p-value? Maybe we should pick a better p-value. But it gives us a simple conceptual change. So if we want to know about the least promising rejection, then we're asking about the last rejection, the rejection with the largest p-value. Okay, so our contributions first, we have a new criterion for evaluating how well a multiple testing procedure does on this metric, where we're looking at the last rejection or the least promising one. So here we can define. So what we're interested in is how promising is the least promising rejection. So we look. If script R is our rejection set, we're going to look across the rejection set and ask which one has the largest posterior probability of being null. And when we take the expectation of that, we call that the max LFDR of the procedure. So that's our new criterion. Our new method is we're going to define a new method we'll call the support line procedure, where we reject the R smallest p-values, where we take R by just taking the minimum of this function. And we'll see this is closely related to the BH procedure. And under a Bayesian model, we're going to show that this procedure actually exactly controls this max LFDR criterion at level pi0 times Q, similarly to how the BH method exactly controls the false discovery rate at level pi0 times Q. And it'll be under the assumption that we have null proportion pi0 and that the alternative density is non-increasing. Okay, so first I'll tell you about what our procedure is. So our basic setting, okay, so we have hypotheses that we'll say HI is equal to 0 if the IF null is true, and otherwise HI is equal to 1. We've got some p-values. And we call script R our rejection set, and then capital R is the number of rejections. And capital B is the number of false discoveries, so the intersection of the number of rejections with the set of true nulls. then our false discovery rate is just the expectation of this ratio. All right, and so now we introduce a two groups model where independently for each index, we assume that each hypothesis has a pi0 chance of being null. And then conditional on HI, which has some density little f0 or little f1, little f0 under the null, little f1 under the alternative, and their corresponding CDFs are capital F0 and capital F1. Okay, so marginally the p-values will be IID with these with the corresponding mixture density and corresponding mixture CDF. We'll make an additional simplifying assumption that under the null, the density of the p-value is just uniform, in which case little f0 just becomes identically equal to 1. And we're going to be assuming throughout that the alternative density is decreasing or just not increasing in P. And the corresponding assumption about capital F1 is that capital F1 is concave. Capital F0 is just P, and so also the mixture CDF is going to be concave. Okay, so in this Bayesian model, there is a counterpart, there's sort of an oracle counterpart to the false discovery rate of a procedure, where we can ask, what's the Bayesian false discovery rate, again defined by Efron et al. What's the Bayesian false discovery rate for p-values that are below some threshold t? So we can ask, in the tail of p-values below some threshold t, what's the probability that hi is equal to 0, given that its p-value is smaller than that value? And it's simple to calculate just by Bayes' rule that this is just the null probability, the cumulative null probability there, and this is the cumulative mixture probability. And then Efron et al. Also defined as counterpart the local false discovery rate, which is instead of conditioning on p being below the threshold, we just condition on the value of p. We don't just observe in a real problem. We don't just observe that a p-value is below some threshold, we actually observe its value. And so it's, I would argue, more relevant to ask what's the probability this particular p-value is null, and that's going to be the null density divided by the mixture, the null component of the density divided by the mixture density. Okay. So we can plot, so if you've seen this sort of p-value plot, I should have explained it better before. So apologies. This plot is a familiar plot for the BH procedure where, as a function of the index, we just plot the order statistics, the increasing order statistics of the p-values. And so then down here, this plot, which is basically taken from Efron's book, is showing the population version of the order statistics plot. So here, as a function of the mixture density, we're plotting this pi0 t, the fraction that are below, the fraction of nulls that are below. Okay, so this is like the population version of the plot that we saw before. And then the Bayes FDR in this model is exactly the slope of this secant line, and that justifies the BH procedure. So it's not hard to show that the local FDR is the slope of the tangent line at the same point. And so in general, if this function is convex, so because this is sort of a reflection of the CDF plot, then the concave CDF corresponds to this plot being convex. If this plot is convex, then both of this both the Bayes FDR and the local FDR are going to be increasing in T. And the local FDR is generally the sort of like marginal utility of a rejection, the marginal quality of rejection. The local FDR is going to be larger than the Bayes FDR. Now, to make this plot, we need to know pi0. So the first thing that we could do, we can either estimate pi0, or we can just bound pi0 less than or equal to 1. So if we just bound pi0 at 1, then we're stretching out this plot. And now this Bayes FDR just becomes pi0 times the slope of the secant, and the slope of FDR is pi0 times the slope of the tangent. All right. And so now, so again, what we would like to do is we would like to find the value. If we knew this black curve, then we would just take the value of t such that this tangent line is whatever it is that we want it to be. But of course, we don't know what f is, so we can plug in the empirical CDF. So now the empirical CDF, this is the proportion of p-values in 0 up to t, the observed proportion of p-values, and then this is the proportion of nulls that we expect, 0 up to t. And so the BH procedure is taking the FDR, is estimating the false discovery proportion by just taking the slope of the secant line. It's estimating the false discovery proportion of using a particular threshold t by just taking the slope of the secant line through the ECDF at that point. All right, and so then the BH procedure, it draws the secant line to be the target false discovery rate, and then it just traces down the secant line as we reduce the threshold until we get to our desired false discovery rate, and at that point we stop and we reject the p-values that are below that threshold. So that's the BH procedure. But one thing that we might note is, again, so as we've been talking about, we can estimate the false discovery proportion for our entire rejection list, or we could break our rejection list into two parts. We could ask, what do we think is the false discovery proportion of the false discovery rate of the first half of the rejection, or what's the false discovery rate of the second half of the rejection? By using the exact same principles that we saw before. And what we'll see is that, so this false discovery rate looks a lot better than what we were asking for. The slope of this secant line looks much better than what we were asking for, but the slope of this secant line looks worse. So the FDP of the last 50% of the rejections is larger than what we asked for. And if we break it up into the last 25% of the rejections, then the false discovery rate looks larger still. Okay, so so what we would like really is to, if we want to know sort of what we're really interested in is what is the false discovery rate near our threshold. And so we might be interested in breaking this line more and more and more. But of course, at some point, that's going to become too noisy of an estimator. That's because the ECDF are not differential. Okay, so now the idea is instead, so we've assumed that the true CDF is concave. So because the true CDF is concave, then we actually can use a better estimator of the CDF. We can take the least concave majorant. So this is the Grenander's theorem. If we take the least concave majorant of the ECDF, then this is the non-parametric maximum likelihood estimator, overall concave CDFs. And we also get out of that an estimate of the density, piecewise estimate of density. And so this gives us empirical Bayes estimator proposed by Strimmer. And the empirical Bayes estimator is where we just plug in this Grenander estimator of the CDF. So what does that look like over in this plot? So if we plot, so again, because we've reflected this plot of this is a reflected plot of the CDF. So assuming that the CDF is concave, we're again going to find the least convex minorant. And so the least convex minorant here is just this dotted line. So we see that it goes between points like this. So it sort of traces out these points. Okay, so now the way that we're estimating the local false discovery rate at such a point is by looking at the slope of the tangent line. So now suppose that we want to, instead of estimating the local false discovery rate, what if we want to actually control the false discovery rate? So now, again, we have our target slope, Q, and we can just move it down until the point where that target slope coincides with our estimate of the slope of this reflected CD. So now you may also notice that we can actually, we would have gotten the same value if we had just dropped this least concave minor inch. And it would still, we could still take this value and drop it down, and it would also be the support point of the ECDF without going through this Grenander estimator. And so we don't actually need to go through the Grenander estimator, it's just the interpretation. So now our estimator is just the support point of the ECDF for a line of slope Q. So again, another way that we can do this is we know that the support point is going to happen at one of these corners. And so all we have to do is we have to take, so we look at each of these points and we find the point at which sort of this distance is largest. And that is exactly equal to the minimizing value of this difference. Okay, so we call our method the support line procedure. So again, so roughly speaking, where the BH procedure is using the slope of the secant line through the ECDF to estimate the false discovery rate, and then cut off the procedure when the false discovery rate is approximately equal to Q. Our method is doing the same thing, but with the tangent as approximated by the support line. Okay, so this is our support line procedure, and so this is just a simple definition. Or it's not hard to show that equivalently, we can just sort the p-values, and again, taking p0 equal to 0, we reject the r small p-values, where r is just the minimizer of this difference. Now we can compare this with the BH procedure. So the BH procedure is looking at these same differences, but the BH procedure is taking the last time that this difference is negative, whereas we're taking the minimizer. So it really is very closely related to BH. And so in particular, for any value Q, as you may have seen from the plot, the number of rejections from our support line procedure is going to be less than the number of rejections from BH, and will make 0 rejections if and only if BH makes 0. So it might sound like our procedure is more conservative than the BH procedure, and indeed it is if they're both run at the same value of Q, but I don't think that's quite the right interpretation, because we wouldn't be controlling the local false discovery rate at the same level as we would want to control the false discovery rate. So controlling the false discovery rate, the average quality of the rejections, controlling the false discovery rate at 5% would typically correspond to controlling the local false discovery rate at a significantly higher value. Okay, so that's our support line procedure. Let me just pause for questions.
So does that Grenander estimate, that's just different, that's different than the empirical estimate, right? Is it?
So the empirical, the empirical CDF is just this broken line here.
What's the Grenander one?
The Grenander estimator is this dashed line, which is the least concave minor, or up to reflection, because I'm not plotting I'm plotting the argument against the CDF. Okay, so next I'll talk about the properties of our procedure. So from what I said, you may believe that the oracle, that what we would really like to do, if we actually could calculate these local FDRs, if we didn't have to estimate them, if we could just calculate them, then we would just reject all the local FDRs that are below some value. That would be the largest, that would give us the largest rejection set, except that all of the local FDRs are below Q. where the maximum, let's say, we'll define the maximum of the empty set as 0 by convention. So this brings us to our error criterion, which is just to say, we're going to say that we control the max LFDR at level Q if the max LFDR of this rejection set is less than or equal to Q. And so the oracle procedure in particular would do this. Okay, so this max LFDR has a nice interpretation. So in the two groups model, the regular FDR is exactly the probability that a randomly selected rejection is null, where we define this event not to have happened if there are no rejections at all. So there's an event that either there are no rejections, that there are some rejections, and it randomly selects one of them as well. The probability of that is exactly false. So our max LFDR is actually the probability that the least promising rejection is exactly this, where again we say that the least promising rejection is not null if there are no rejections at all. And if we have a decreasing alternative density, then we can actually say we can replace our least promising rejection with just the last rejection. The rejection where this notation means the rejection whose order statistic is the order statistic of the number of rejections. Yes.
What is the expectation taken with respect to again? There.
Yes. So this expectation is just taken with respect to the procedure. So we sample the hypotheses, we sample the p-values around the hypotheses, we sample all the data, and then we run our procedure, and then there is some largest false discovery rate from among all the rejections. Or equivalently, we can then ask, let's say we pick the last one, and is that last one also a null? And it would be the same. It would be the same kind of thing. Okay, so controlling the max LFDR, the probability the last rejection is null with decreasing F1 is going to imply that we are controlling the probability that randomly selected rejection is null. And FDR control also in particular applies we FWDR. Although again, this relationship is only max LFDR control at the same level as FDR control when, again, just to point out, we would typically be running LFDR control at a larger level than we would be running FDR control. So a standard convention from suggested by Efron is to run max LFDR control at 0.2. Sorry, to not control is to use 0.2 as a cutoff for the LFDR. Okay, so all right, so our main result is that under this two groups model with uniform nulls, we have that the probability of the last rejection, or equivalently the max LFDR, is exactly pi 0 times Q. And furthermore, if the density is the alternative is non-increasing. Oh, I'm sorry. So this is always true. And if the alternative density is non-increasing, then the probability that the last discovery of the false discovery is the same as the max LFDR. The last one is the least promising. So again, so this theorem holds. So the procedure operates without any knowledge of F1, except for the shape constraint. But we have this result regarding. Okay, so again, we can compare in the context of one of the simulation settings of Benjamini-Hochberg with 64 hypotheses. We can compare false discovery rate with the max LFDR. So if we compare the BH procedure with the support line, and I'm sorry, these colors are reversed. The red one is the BH procedure, and the blue one is the support line procedure. Then what we see is, so if we run them on if we run them both on input level Q, then the BH procedure, the red one, will achieve exactly FDR control at exactly the level pi 0 Q, whereas the support line procedure will control FDR at some smaller level. As if we go over and we ask, what's the probability that the last rejection is false? The support line procedure controls it at exactly the advertised level as proven, but the BH procedure is, it's not that it's anti-conservative, it's, it's just the probability that the last rejection is false is much larger than the level Q. Now, again, this is not saying that the BH procedure is wrong, because the BH procedure doesn't advertise that it controls this quantity at level Q. But for example, if we run the BH procedure at say 0.1, then we get something like 32% chance for the last rejection. Yes.
Well, I just have a question about the assumption of F1 being increasing.
Yes.
How
Being decreasing.
decreasing, sorry. How stringent is that assumption?
Okay. So how stringent is this assumption? So essentially, this would be true for this is true in almost every setting, and the reason is that it's equivalent because the ratio between F1 and F0 is the sort of Bayesian evidence against the null. The evidence should be decreasing with p-value. Smaller p-values should be stronger evidence against the null if you set up the p-values right. So in a Gaussian problem, or in any kind of exponential family problem where we have monotone likelihood ratios, this would be the case, and it will be the case for those settings. Okay, so again, we run BH at level 20, then we get max LFDR control at level 54% or something. And we could get max LFDR control with the BH procedure by running it at level 6%. So it's not that we can't control max LFDR with the BH procedure, but it says by running it at some lower level Q. But we don't actually, but if we change the problem parameters a little bit, then we might need to run the BH procedure at level 0.3 or something. And so in general, we don't know what level we could run the BH procedure at. We're not going to know the correspondence between what level to run the BH procedure at to achieve a certain accelerator. Okay, so basic proof sketch. So here what we want to prove is that the probability that the last rejection is false is exactly pi 0 times Q. So first of all, since these p-values are identically distributed, we can just take this probability and we can replace it with m times the probability that any particular one of them is the last rejection and is a false rejection. So now we can take this event and split it into first the probability HM is equal to 0, that's pi 0, and then the probability that the last rejection is this p-value is the last rejection given HM. And so we get this, and so now the question is, what is this probability? And so the main technical lemma in the theorem is that actually for any fixed values that the other p-values could take, if PM is uniform, 0, 1, then, or actually really just for any fixed values that the other p-values could take, the Lebesgue measure of the set where PM is the last rejection is exactly equivalent. So this is just a basic result of how the procedure operates. I would say it's non-trivial why this is the case. So it follows from an analysis result of Takachi. And it has to do with just sort of how the rejection set changes as we hold m-1 of the p-values fixed, and we move the other one from 0 to 1. Okay, so then this in particular shows that this conditional probability is going to be exactly Q over M, and so we end up with pi 0. So we have this finite sample result, but we can also we also have a result on the asymptotic distribution, and essentially, so we can ask, how does this actually behave? And so we can say that the threshold that we find, so this is the threshold that we actually use, tau sub q, minus the threshold that would actually make the LFDR exactly equal to pi 0 q. So this is what we would use. This would be the oracle threshold, and the threshold that we actually use converges to the oracle threshold at a rate m to the minus 1/3. So it's a non-parametric rate because we're using, in effect, we're using this Fernandez estimator. Converges at a rate m to the minus 1/3, and also the attained LFDR at the threshold converges to pi 0 times q, again at some rate m to the minus 1/3. We have explicit constants, and then this distribution, Chernoff's distribution, it has to do with the probability that a random walk, sort of the distribution of the maximum of a Brownian motion with quadratic drift. But it's roughly a scaled version of normal. Okay, so as a result, we can say that the max, the actual attained, not the expected, but the actual attained max LFDR among all the rejections is approximately pi 0 q plus something like that, minus 1/3. Yes.
One quick question. I think I probably missed that. So what's the reason that you have cubic rate?
Oh, so it's just because we're looking at it's because of the non-parametric nature of the problem. It has to do with how the ECDF converges to the CDF. So here, this is where we assume that f is decreasing at this value. So the true CDF has some, second derivative there. But the convergence of the ECDF to the CDF looks sort of like a Brownian motion. Yeah. All right. So we can ask, so how good are these bounds actually? So again, looking at this example from the PhD paper, what we can see is that the max LFDR, so this is coming from our asymptotic calculation, and then this is just coming from simulation. So from our asymptotic, this is actually coming from our calculation from simulation. But the asymptotics are given by the x's. So the asymptotics for at least the interquartile range are almost dead on for 1,000 hypotheses, which is not that large of a problem. But here we see, so the attained, if we ask for a 0.1 LFDR, the attained LFDR is going to vary around pi 0 times 0.1 by a little bit. Okay, so all right, so next, we also, so this whole thing depends on pi 0, but we might not want to control the LFDR at pi 0 times q, we might want to control it at some value q. And so we can use Story's estimator at pi 0. Some value zeta, say we take zeta to be 1/2, then we say basically, if we're getting this finite sample correction, it would essentially be like 2 times the fraction, 2 times the fraction of p-values that are above 0.5 would be a reasonable estimator of the normal function. And so then we can just plug in, this value, and we can prove that this procedure also controls the max LFDR, but now at less than or equal to 1 q. And under some conditions, the max LFDR is converged. Okay, so we talk a little bit more about decision theory. So again, so before we sort of motivated this problem by talking about some kind of trade-off between false positives and false negatives. So suppose that we have a cost benefit exchange rate of lambda. So suppose if lambda is 4, then this is saying that a false discovery is as bad as missing 4 real discoveries. So we're willing to accept 1 false discovery per 4 real discoveries. And so we can write the actual cost as by this weighted classification loss, which is going to be this cost benefit exchange rate lambda times the number of false discoveries minus 1 times the number of false non-discoveries. Minus 1 times the number of true discoveries. And so we pull out this V, and so we get exactly this formula. And so it's a short calculation to show that in this case, the way that we maximize this, if this is our loss function, the way that we minimize our risk is to just reject all the hypotheses whose p-values have LFDR less than alpha, where alpha is just given as a straightforward function of the lambda that defines our trade-off. So while Efron suggests using about 20% as the value at which to use the local false discovery rate, in fact, we don't need a standard because it actually just comes straight out of our loss function. Okay, so the cost benefit analysis directly guides the choice of this threshold. All right, so now suppose that we have the max LFDR is bigger than alpha, and the LFDR is non-decreasing, then we can actually improve the method by any method whose max LFDR is bigger than alpha, we can improve it by dropping the last rejection. So then the procedure that does this procedure then drops the last rejection will actually have strictly better risk. And I'll skip over this proof. All right. We can also interpret our method as estimating and minimizing a plugin estimate of just this loss. So if we wanted to estimate this loss, we could say, well, first of all, R over M, for a particular threshold, the number of rejections divided by M, that's just Fm of T. And 1 plus the number of false rejections divided by M. Well, we don't actually know, but we can guess that the number of false rejections below T is going to be approximately pi0 times T times M. Okay, so we divide it by M, we get pi0 T. So this is just a simple plug-in estimator, and then we replace this with 1 over alpha. And so our support line procedure, if we take Q equals to alpha, then we're actually doing exactly this, but we're replacing pi0 with 1. So this becomes the minimizer of the loss where we're approximating pi0 by 1. All right. So we can also ask about the regret. So now that we've defined, yes.
For the estimated loss, you need to make sure that it's positive, it's always positive.
Oh, so because when we plug in T equals 0, then we're always going to, then it's going to be 0. So the worst, so if this loss always appears to be positive, then we just plug in, then we're just going to use T equals 0. Okay, so now we can ask, well, actually, what kind of regret do we have from this? So if we compare the Oracle procedure that actually knows what the LFDR is, and we compare our procedure, then we can also show that the regret, if we run our procedure knowing pi0, then we divide alpha by pi0, so that gives us a slightly more liberal value of alpha. If we run our procedure with the Oracle value of pi 0, then the regret, again, it's going to shrink at a factor at a rate m to the minus 2 thirds. Okay, so this also works with an estimated pi 0 hat, provided that pi 0 hat converges to pi 0 factor. Okay, so we can make this plot. Okay, so here, this is the asymptote based on just this. So this is just a constant times m to the minus 2 thirds. And we can compare the observed regret for both the procedure with oracle pi 0 and the procedure with estimated pi 0. And they both look pretty close to the asymptote. Whereas if we just bound pi 0 by 1, then we're going to have some asymptotic risk. We're not going to converge to the right rejection. Okay, so our method, so we could ask again, so how bad is it if we were to just use, what would the regret be if we were to just use alpha instead of alpha over pi 0? We'd like to use alpha over pi 0, but if we just use alpha, how bad is it? And so in this plot, we see that the regret is actually quite small for using a slightly wrong alpha, but still, so we're still targeting the right metric, the local fault discovery rate, but just at a slightly wrong value alpha. Whereas if we run BH, we're targeting the wrong metric, we're targeting the false discovery rate, and so we might get lucky and we might choose a value of alpha, or we might choose a value of Q such that the BH procedure gives us, it is the perfect value, the perfect value of Q. But what is the perfect value of Q is going to depend on the signal strength. So here we have some parametric model for F1, and depending on the value of theta, the right value to use for BH could vary a lot. And so there's no value. We can't just take, say, alpha over 2 or alpha over 10. Right. So we want to control L, if we want to control LFBR at level 0.2, we can't just, it's not a good general rule to say we're going to run BH at level 0.25. Okay. So, okay, so to motivate the next part of the talk, let me just talk a little bit about to change gears a little bit, talk about the nudge meta-analysis. So a nudge is a particular kind of psychological study where we try to sort of change people's choice architecture so that it'll change the decision that they make, at least with some probability, but without actually forcing them to change their behavior. So maybe we, by default, enroll them in some retirement savings plan that they can always opt out of, but we make it opt out instead of opt in, and more people are likely to do this. So a couple examples. For one study in this data set, a parent chooses a breakfast option for their child, and there might be a sort of a default choice, which is very healthy, but they're allowed to switch to an unhealthy option, or vice versa. There might be an unhealthy default option, and they're allowed to switch to the healthy version. So here, even with a small study, there's a huge effect of the probability that they choose the healthy option. So under the treatment, they're 80 percentage points more likely to choose the healthy option. So here we have a huge test statistic, a huge t statistic, even with a small sample size. So another study, the driver is prompted to become an organ donor when getting their license renewed. So in the UK, you renew your license, and then they ask you, do you want to become an organ donor? Some people are already organ donors. Among the ones who aren't, it's unlikely that they're going to choose to become an organ donor at this particular moment. So the probability, the overall probability is very small. But they can make it a bit bigger by adding this text, say, if you needed an organ transplant, would you have one? If so, please help others. And so it turns out just this language, it doesn't increase by a lot of percentage points, but it increases the probability by a factor of about 35%. So both of these probabilities are very, very small, they're less than 1%, but because they have a huge sample size in this case, they are able to actually detect this effect.
You know, actually, your house,
What's that?
you know, the actual.
I think it's like 0.8%. Yeah. Okay. But this did correspond to, they said this treatment effect size corresponds to like 90,000 additional registrations per year. So on an absolute level, it's actually pretty large. Okay. So anyway, so Mertens et al. Had a meta-analysis combining data from a lot of experiments like this. And so they ran a meta-analysis to ask the question, do nudges work? They found a positive overall effect of nudges. There was some controversy. People wrote back in and said, if you adjust for publication bias, then there's no evidence for nudging. There was a discussion about this. I think was a little bit unproductive because they're asking the wrong question. The right question isn't whether nudges work overall. There's many different nudges. Like the two examples I showed you are very different. And for each of them, there is very, very strong evidence that each of those work. There are other nudges in the data set that didn't work. So a more sensible question, I would say, is which nudges work? And so we can just have some hypothesis, which is, we'll say HI is equal to 1 if the nudge has the desired effect, and HI is equal to 0 if it has no effect or maybe even a negative effect. All right, so we can ask, maybe we'll just look at the significant studies. And we can ask, what's the FDR for the significant studies, or for which studies should we be convinced that they have positive effects? So first of all, we can not have to worry about publication bias if we just look at the significant studies. So at least if we think people are always willing to publish a study if the p-value is below 0.05, then we can really at least think that the nulls among the significant studies are really uniformly distributed, 0 to 0.05, or in this case, 0 to 0.025, because we're looking at right tail p-values. So we just take them and we multiply them by 40, and now we've got uniformly distributed conditional p-values under the null. And so we can estimate the false discovery rate of this group by just taking what fraction of them are above 0.5, multiplied by 2, and we can estimate pi0 hat at about 28%. So most of the significant studies probably did correspond to true effect, which is also, we would also conclude by looking at this. But maybe we would like to find how small do we have to take the threshold before 10%, before only 10% of the p-values below that threshold are null. So we might want to ask how small of a p-value should we demand before we're willing to believe in the study. The one way we might do that would be to use the BH value. And if we choose the tau BH at 0.27 or 0.27 over 40 on the original p-value scale, then we think only about 10% of them are false discoveries. But again, looking at this plot, we have a very good idea of which 10%. So the fact that this list has 90% true discoveries and only 10% false discoveries, it doesn't really vindicate our decision to believe in these studies. So again, we might plot this sort of p-value order statistic plot. And so again, it's based on the slope of the secant line that we're making our 10% estimate. But again, we can break this up. If we go a little bit further to the right, now we've got a 22%, 28%, or even 40% estimate for the fraction of false discoveries near the threshold. And we can make this kind of broken line procedure, but we might want to ask, so if we take this to be smaller and smaller, we might want to know, what is this false discovery proportion estimating? Now, interesting question here is, we've been talking about a Bayesian two-groups model, but it's sensible to talk about estimating the false discovery proportion without appealing to a Bayesian model. So the BH procedure is not assuming any kind of Bayesian model. So what are we actually estimating here? And I'm almost out of time. So let me go through this quickly. So assuming we have a fixed effects model. So now the alternative p-values have some continuous CDF on 0 and 1, and the null ones are 0. Okay, there's some compound decision theory story here. But we can, but I think the more interesting story here is we can just talk about the sort of false discovery proportion within some interval. Not just the false discovery proportion from 0 to t, but we could talk about the false discovery proportion between s and t. And we might ask among the p-values in some interval s to t, what fraction of them do we think are null p-values? So we expect to find about t minus s times pi 0 nulls in that interval. And so if t minus s times pi 0 is 5, and we actually find 30 p-values, then we might think, well, therefore, probably about 1/6 of the p-values in this interval are nulls. Again, there's no Bayesian assumption here. And then there's a sort of interval, this interval PFDR. And so what we can show is that, so again, if we just shrink this interval down to a point, we just get a continuous version, which is exactly equal to pi 0. Pi 0 just being the finite fraction of p-values that are actually uniformly distributed. So there's m0 uniformly distributed p-values and m total p-values times the average density of the null ones divided by the average, the sort of average density of all m. Another interpretation. So an interpretation here is to say if we see a p-value near this threshold t, then what's the probability that that p-value is a null p-value? We don't need a Bayesian model for this interpretation because it's a random subset. It's a random subset of p-values that actually get into this interval. And if we had, and so in the limit, we can ask about what's the probability given that some p-value is exactly equal to 0.001. Given that some p-value turns out to be exactly equal to 0.01, the index for which that happens is a random index. So as a result, the hypothesis for which its p-value lands exactly at 0.001 is a random hypothesis, even though we had m fixed hypotheses, h sub capital J is a random hypothesis. All right, so I don't want to go too much over time, and so I will just go through the rest of this. So apologies. And so just to conclude, so we have a new criterion, which is the expected maximum local false discovery rate across the entire rejection region, or across the entire rejection set. A new method where we are going to reject the RQ smallest p values based on this rule. We call this port line procedure. And under a Bayesian two groups model, we can prove that our method controls the max LFBR at exactly pi 0 times q, and with the regret, which is shrinking like n to the minus 2/3. And so soon we have an interpretation of this procedure in the frequentist model, where the local false discovery rate is no longer has a Bayesian interpretation, but is rather just referencing sort of the local frequency of nulls near t. So again, apologies for going over time, and thank you very much for having me. Other questions? Yes.
Well, I have a more applied question. So, well, we try to work with collaborators, try to control FDL. FDL usually take a computation-based approach. So the reason is for twofold. For the first one is that p-value is never uniform under our distribution, and because it's a model data complicated, then it's hard to find the correct statistical model for that. Second issue that the covariates are always highly correlated. So we usually just do a permutation, constraint our distribution, and then you estimate that that way. And so that we have been using that for a while, and that seems to be a simple strategy. I was wondering, the new method you provide over here, whether I can, what kind of benefits here that I can convince my collaborators to take on.
So right now, I think we're kind of in the early stages here. So it sounds like in the procedure that you have, first of all, the independence assumption would probably not be justified. Is that right?
Right.
Yeah. So we're working on a follow-up method with correlated p-values. But I'll get back to you.
Thanks.
Yes.
Two quick questions. So the first one is just on the two-group model, you had a spike at 0, and I was just curious how sensitive, like, if you made it not a spike, but like actually sort of locally near 0 effects, like how sensitive the method would be to like slight deviations from that.
You mean in the very, very first sort of.
Yeah,
first
that very
example?
first, yeah.
Yeah, so in that very first example, I think you would basically see the same thing. So in fact, that kind of thing is. So this example is not. Okay, so this example is not. Is not nearly as perverse, but still, we're not sort of controlling the average false discovery rate at 0.1, but the estimated false discovery rate sort of near the threshold is 0.4. And as the alternative gets more and more and more concentrated near 0, if the alternative density near the threshold is relatively small, then so if the alternative density at the threshold is exactly 0, then you would have a local false discovery rate of 100%. And if it's small, then you might have a local false discovery rate close to 100%. Because pi 1 is also going to be fairly small, right? So if say the alternative density is below 1 at the threshold, then the local false discovery rate is going to be probably higher than 50%.
My second question was just more about the nudge example you were giving.
Yes.
So I agree that the question they're asking of nudges work is not a little too general.
Yeah.
But often when I talk to people about nudges, it's like what type of nudges work, not whether a specific one. So I'm just curious if these types of methods, like, can I think?
Yes. So we could definitely break out this analysis for subgroups, for example. But yeah, I think what we would really want to do there would take more of a kind of regression modeling approach, right, to estimate the local FDR as a function of the. I think that would, I would definitely endorse estimating the local FDR as a function of covariates and a p-value. This is yeah, so I've worked on a lot of methods that do that, but I don't think we're anywhere close to having like a nice exact finite sample result for the local FDR control. We could give you finite sample results for FDR control. That's a lot easier, but for local FDR control, we're not particularly close. Thanks.